Okay, so let's get this started. Welcome to our video report on Experiment 8A Qualitative Analysis. So what is qualitative analysis? Well, it is the process of determining the substances or elements present in a sample through a series of tests, which ultimately results to finding out what the sample is. Do note though that it is only limited to tell what substances the sample contains, not how much of a certain substance it contains. Here we see the four basic areas of experimental inquiry. First off the list is the physical property of compounds. This means that we are observing the substance based on its appearance, color, texture, odor, and things like that. Next is classification by solubility, in which we dissolve the sample into various solvents and see whether or not they dissolve in that specific solvent. Take, for example, we dissolve the organic sample in water. If the sample dissolves in water, this tells us that it is a low molecular weight polar organic compound. If it does not dissolve, well, we test it in some other solvent, say ether, and well, depending whether it dissolves in it or not, it tells us something more about the sample. It tells us something more about the sample. Up until the point when we figure out what functional group it belongs into. Yes, it only tells us the functional group present, not what the sample is. Next is elemental analysis. On this part, we perform the process called sodium fusion, in which we burn or heat a clean sodium metal in a test tube. Then we put a good amount of the sample into the tube and fuse it by heating it once more. We then dip the red hot tube into the water, causing it to shatter. Afterwards, we boil the fusion solution so that we are sure that it is completely dissolved. Finally, we filter it and we perform the usual qualitative tests to figure out the possible constituents. The idea behind it is that when an organic compound is fused with sodium, when any halogens, nitrogen, and sulfur will be converted into their respective inorganic sodium salts. On a side note, this process was made by Jean-Louis Lassagne, a French chemist whom we won't bother to discuss any further, as he is not very much related to the discussion. Well, okay, let's get back on track now. So the last on the list is classification test for functional groups. Basically, we react the sample to a reagent which should give a specific visible result, indicating the presence of a certain functional group. In this experiment, we shall test for unsaturation, aromaticity, acidity and basicity, and alkyl halides. Before testing for unsaturation, we will be making our own acetylene gas by following this setup. First, we put a piece of calcium carbide into a distilling flask. At one end of the distilling flask, we place in some rubber tubing. Then, on top of the distilling flask, we place a separatory funnel fitted with a port by the mouth. Distilled water is placed into the funnel afterwards. This thing right here is just a basin filled with water. Inside the basin are the test tubes we will be filling with acetylene gas. The process here is that we will let the water slowly trickle into the flask. Upon contact with the calcium carbide, acetylene gas will be formed. As soon as we observe this, we place the rubber tubing into the test tube and invert the test tube in a vertical manner in such a way that the mouth is still submerged. The gas will then pass through the rubber tubing and into the water-filled test tube. The acetylene gas will then displace all the water in the test tube. Finally, we fit a cork in the test tube and we have acetylene gas in a tube. While making acetylene gas, keep in mind not to be working near hot stoves or fires, because if we did, well, we might blow the lab and, more importantly, ourselves up. So be careful. Okay, so getting back into the discussion. Now we will be testing for unsaturation by reacting a reagent with 2% bromine and a methylene chloride or dichloromethane solution. In here, we test acetylene, benzene, styrene, and hexane for unsaturation by placing a few drops of the 2% bromine in dichloromethane solution. The decoloration of the bromine indicates a positive result. Here we have the results of the test. On acetylene, a brown precipitate is observed as a result and a rugby-like smell is released. It's not really advisable to smell though, as you might get high. The same is observed in styrene, although without the funny smell. On benzene and hexane, nothing is observed other than two distinct layers, one violet and the other clear. Okay, so it's really interesting that nothing happened with benzene, because as you might know, benzene is unsaturated and yet we observe nothing. So does that mean the benzene we tested on isn't really benzene? No. The reason that we didn't see any results is because benzene behaves both as a saturated and an unsaturated compound. The delocalized double bonds present inside the molecule make it much less reactive than more discrete double bonds, as such found in ethylene. This makes it behave more like a saturated compound, preferring substitution reactions more than addition reactions, since the latter reduces the resonance stabilization energy. Well, wasn't that interesting? Now getting back on topic. The next test for unsaturation is the Bayer's test. Using the same set of reagents in the last test, we put a few drops of 1% aqueous potassium permanganate in each tube. The decolorization of potassium permanganate from purple to a lighter color and the formation of dark precipitate indicate a positive result. Our results in this test are similar to the ones with a 2% bromine solution, with acetylene and styrene showing positive results and negative for both benzene and hexane. Here we simply say that unsaturation is the reduced capability of a carbon atom to bond with more atoms due to the presence of multiple bonds such as those found in alkenes and alkynes. This here is the mechanism for the alkenes and the alkynes. On the alkenes, see that the double bond or pi bond is broken and is then replaced with bromine at the trans positions. For the alkyne, we see that reacting it with some bromine results to the breaking of a pi bond, turning it into an alkene with bromine at the trans position. Then, when more bromine is added, another pi bond is broken and the freed up positions are further filled with bromine. In general, this process is called halogenation. Here, we see what happened with the reaction of the 2% bromine solution with our reagents. Initially, bromine is a red liquid. However, when it is added to an unsaturated compound, a colorless dibromide is formed, thus showing a positive result. Take note that for this reaction to occur, the pi bond must be sufficiently electron-rich, thus the presence of the activators would hinder the reaction. Also, unsubstituted aromatic compounds, like the ones mentioned earlier, like benzene, do not react with the bromine because of the same reason stated earlier. In here, we see the reaction mechanism for alkenes and alkynes with the Bayer's test, which uses an aqueous potassium permanganate solution. With an alkene, the pi bond is broken. With an alkene, the pi bond is broken and hydroxide ions are attached at the cis position. Also, the brown precipitate seen is composed of manganese dioxide. With an alkyne, the reaction is pretty much similar with the alkene reaction. All pi bonds are broken and are then attached with 4 hydroxide ions. This reaction in general is what is called a redox reaction, which is the shorter term for oxidation and reduction reaction. Here it is made clear to us that the potassium permanganate acts as the oxidizing agent, as it is the one helping the alkene or alkyne oxidize by undergoing reduction. The reduced product is the brown precipitate manganese dioxide. This reaction's significance is due to its ability to react only with alkenes and alkynes, and not alkanes or aromatic compounds. So there, we finished the test for unsaturation. We now proceed to the test for aromaticity. In the test for aromaticity, several drops of cold concentrated nitric acid is slowly dropped in a test tube containing cold concentrated sulfuric acid. The test tube must be in a beaker containing ice-cold water. This is necessary because the reaction between the nitric acid and the sulfuric acid is highly exothermic. Afterwards, we add several drops of toluene into the acid mixture and heat in a 50 degrees Celsius water bath for 5 minutes. Finally, we pour the mixture in a beaker containing ice-cold water. A yellow-colored solution and an aromatic odor indicates a positive result. Seen here is toluene, an aromatic compound. Since we observed a positive result, we can be certain that we have successfully made nitrotoluene. We have mentioned aromaticity for quite some time now, thus it would be best to define it. Aromaticity is defined as a property in which conjugated ring of unsaturated bonds, lone pairs, or empty orbitals exhibit a stabilization stronger than would be expected by the stabilization of conjugation alone. This may be quite complex to understand, but as the internet seems to say, there is no simpler definition for it. So just take it in for what it is, and hopefully it's not very confusing. Moving on. Here we see the mechanism called nitration, which is essentially just what we performed earlier. As we can observe, the hydrogens are only being substituted by the nitro group. This happens because the nitro group is a stronger electrophile. This reaction in general is called electrophilic aromatic substitution. We can also see that the formation of the ortho and para products are more preferred than the meta products. We can also see that the formation of the ortho and para products are more preferred than the meta product. This is because the resonance form for the rate determining intermediate of the ortho and para positions are tertiary carbocations, while the meta position is a secondary carbocation. Tertiary carbocations are formed faster than secondary carbocations, thus the reason for why the ortho and meta positions of nitrotoluene are the major products. Here we have a simple summary which would be good to keep in mind. Benzene derivatives react pretty much like benzene but with some minor differences. Nitration of toluene generates a mixture of ortho and para positions of nitrotoluene. Reactions of toluene occurring at the ortho and para positions spread the positive charge to 2 secondary carbon atoms and 1 tertiary carbon atom, while with the meta position, the positive charge is spread over 3 secondary carbons, which is similar to the reaction with benzene. Well, that summary was not quite intuitive, but I hope that helped you understand things a little bit better. Anyways, moving on. Well, we're done with the tests for aromaticity. Now let's proceed to the test for acidity and basicity.